Alright, let's turn next to solving a simple linear programming model graphically, and for that we go through an example. So assume that Stats Toys Incorporated produces two toy figures. They are Bernoulli and Nightingales. It's probably some academic toy figures. And both the Bernoulli and the Nightingale toy figure sell for $10. So that's the unit profit. Let's think of it as a unit profit per unit sold. And in order to produce a Bernoulli and a Nightingale, 3 production factors are needed: cloth, glue, and plastic. And below table summarizes how much plastic, cloth, and glue is needed in order to produce one Bernoulli and one Nightingale. And it also shows the total available amount of those production resources. So for example, if you want to produce one Bernoulli, it requires 2 units of cloth, and the production of each unit of Nightingale requires 1 unit of cloth. But we have only 18 units of cloth. So that means we cannot produce 10 Bernoullis because that would require 20 units of cloth, but we have only 18. And the same applies to glue and plastic. So we see the production coefficients and the total available. So now we can take this information and insert it into our initial setup of equations, where we said we want to maximize a function z, like a profit function. And in the previous slide we said a times x1 plus b times x2. So now the first decision variable x1 is the Bernoullis. The second decision variable is the Nightingales. So how many shall we produce of them? And a and b, those would be the unit profits. And in order to maximize that function, we are constrained by the cloth constraint, the glue constraint, and the plastic constraint. And what you can see is the production parameters from the table. They now enter these constraint equations, like 2b plus 1n must not exceed 18. So if b were, for example, 3, then we would use up 6 units of cloth, and if we produced 12n, then we would exactly meet that requirement. So if we produce, for example, 3 Bernoullis, we use up 6 units of cloth for the Bernoullis, and if we produce 12 units of Nightingales, we use up an additional 12 units of cloth for the Nightingales. And the same for the glue constraint and the plastic constraint. So now so this is a very simple linear programming model, but it's very useful in order to get the intuition. And what we want to do is we want to solve it graphically. So if you want to solve a linear programming model graphically, you typically follow 4 steps. The first one is that you draw all constraints in a diagram with the decision variables on the x-axis. Then you identify the area of feasible production, or the feasible production possibility frontier. And that is maybe still at this point pretty clear. What might be not clear at this point is that step 3 is to add an arbitrary isoprofit line to the diagram. And then step 4, we shift the arbitrary isoprofit line as far away from the origin to identify the profit maximizing production. So if step 3 and step 4 are not clear yet, don't worry, they will become clear in a couple of minutes. So let's begin with step 1, that we draw all the constraints in a diagram. So here, for example, we had the cloth constraint written as 2b plus 1n is less than or equal to 18. And likewise, we could write the glue constraint that 1b plus 4n must not exceed 20. Well, so here to the left you see a diagram where we put Nightingale on the y-axis and the Bernoullis on the x-axis. So in order to match these constraints, like 2b plus 1n is less than or equal to 18, or the plastic constraint 3b plus 6n is less than or equal to 36, in order to match these equations, that graph, we need to rearrange the terms such that we have n to the left side of the less than or equal sign. And then if we do that for the cloth constraint, so let's just do it for the cloth constraint. So we just say, 2b plus 1n equals or is less than or equal to 18. Well, if I want to rearrange this equation to have n on the left side, I'll just subtract on both sides 2b, and we get 18 minus 2b. And we can do the same thing for the other constraints, but there's even an easier way to do it. So what we could do, for example, we just could ask, if I use up all my cloth to produce Bernoullis, how many Bernoullis can I produce? Well, then you would do 18 divided by 2, that will give you 9. And likewise, so that means the intercept for Bernoulli must be 9. And if I use up all my resources to produce only Nightingales, I can produce 18. So now if we connect 9 or 18 for Nightingale and 9 for Bernoullis, then we get the production constraint, and that doesn't look too good. So it starts at 18, goes down to 9. Okay. And you can see this is basically 18 minus 2b because the slope is negative 2. So now let's see if I can make that a little bit bigger. Maybe outline and maybe weight, make it a little bit bigger. Okay, so this would be our cloth constraint, and now you can already tell why is it called linear programming. Well, it's because we largely deal with straight lines. Okay, let's move next to the glue constraint. And what we can do is we could rearrange again the equation to isolate n to the left side of the equal sign. And if we do that, we will get 5 minus 1/4 times b. Or I'll just say, if I use up all my glue to produce Nightingales, how many Nightingales can I produce? Well, 20 divided by 4, that's 5. And if I use all my glue just to produce Bernoullis, then I could produce 20. So this goes from 5 to 20. The glue constraint starts at 5 and goes till 20. So that would be here the glue constraint. And again, let's also make that a little bit bigger. And the last one is the plastic constraint. Again, we could rearrange 3b plus 6n less than or equal to 36 to n is less than or equal to 6 minus half a b. And again, if we divide 36 by 6, then we get 6, and that means if we only use plastic to produce Nightingales, we can produce 6 Nightingales. So let's do that in blue. So the Nightingale constraint or the plastic constraint starts at 6 for Nightingale. And if we divide 36 by 3, we get 12, so that goes from 6 to 12. Okay, but sometimes it doesn't pick up a straight line. No. Okay. Okay, so now we have all three constraints. And again, let's also make that a little bit bigger. Okay, so these are our three constraints. And the next step would be, what's the area of feasible production? And the area of feasible production is obviously everything which is, if you go from the origin, you go up. As soon as you hit a constraint, well, that is where the frontier ends. So this would be equal to this line, and maybe then this one here, so this yellow line, roughly. So this area here is the area of feasible production, and you can see that a little bit nicer on the next slide. So that's pretty straightforward. So the area of feasible production is given by, or the production possibility frontier is given by the first point that you reach if you go up at any x. Okay, so the next question is, what is the profit maximizing quantity? So let's take a look at this one here more closely. Obviously, I can produce 5 nightingales and 0 Bernoulli. So I can produce this point here. Let's call that A. Well, in point A, I produce 5 nightingales, but no Bernoullis. Because the unit profit for each is 10, the total profit, which I abbreviate with pi A, would be 50. Let's take this point here. I could also produce, for example, 4 Bernoullis and 4 nightingales. So then that would be point B. And they called it profit B. 4 and 4, that would be 80. Let's take another point, maybe this one here, point C. The profit in point C would be I produce 8 Bernoullis, that's 8, and 2 nightingales, so total profit would be 100. And let's take another point, maybe point D. Then in point D, the profit would be I only produce Bernoullis, no nightingales, total profit would be 90. Okay, so it looks like as if the profit maximizing condition is at the profit maximizing point is point C. Well, what we don't want to do is we don't really want to go through all possible combinations, but we want to have a technique which makes our life a little bit easier, and that is what is known as step 3, which is to identify the ISO profit line. And the ISO profit line is a little bit similar to the production possibility frontier. So the production possibility frontier tells you all combinations of producing, let's say, Bernoulli and nightingales that use up all the resources. So if we go back again, we saw if we have 18 units of cloth, well, I could produce, for example, 18 nightingales and no Bernoulli. But, I could also produce 10 nightingales and 4 Bernoulli. So I use up also all 18 units of resources. And similarly, the ISO profit tells us all the combinations of Bernoullis and nightingales that give us the same profit. So we can write that in general terms like this. So the total profit, I call that profit total, is equal to the profit of a nightingale times the number of nightingales that I sell plus the profit, the unit profit per Bernoulli times the number of Bernoullis that I sell. That will be my total profit. Okay, so now if I rearrange again this equation such that I have n, the nightingale, to the left side of the equal sign, I can also write unit profit nightingale times nightingale, that is equal to the total profit minus the unit profit of a Bernoulli times the Bernoulli. And then finally we divide both sides by n, by the profit, the unit profit of a nightingale, and then we get n equals the profit total over the unit profit per nightingale minus the unit profit per Bernoulli over the unit profit per nightingale times the number of Bernoullis. So that will give us here, that is basically the intercept of our ISO profit line, and that here the ratio of the unit profit of Bernoulli to nightingales, that is the slope. Okay, so now the unit profit is, if we, let's write it here, so if we plug in our numbers that we have, the unit profit of a nightingale and a Bernoulli, that's each 10, so we can write the unit profit is n equals whatever I want as the total profit divided by 10 minus the unit profit of Bernoulli over the unit profit of a nightingale, that's 10 over 10, so that's -1 times nightingale. Okay, so now I can substitute. Let's assume the total profit is supposed to be 80. Then the ISO profit line would be 80 over 10, that's 8, minus 1n. So I'll just draw that in here. That would go from 8 to 8. Okay, so that would be the unit profit for a total profit of 80. Well, what if the total profit were 100? Then the ISO profit line, we would insert now 100 over 10, that's 10. And the slope is still 1, so the unit profit would be, the ISO profit line would basically shift to the right and start at 10. So now we have this ISO profit line, and if, let's say, I want to know the ISO profit line for a profit of 120, I would now insert into the total profit 120, then you get 120 over 10, that's 12 minus 1. So that is the total profit, the ISO profit line. That gives me all the combinations where the profit is equal to 120. So now what we have seen is if you shift this curve to the right, you have a higher profit. So now what we do in step 4 is we take this arbitrary ISO profit line and we shift it as far out as we can so that we still touch the area of feasible production. And you see, if you do that, you get to the point where you indeed see that the profit maximizing combination of Bernoullis is 8 Bernoullis and 2 nightingales. And that is what we also saw earlier as we just plugged in random numbers. But this is how you do it. You just create an arbitrary ISO profit line and then you shift it as far out as you can. So that's the idea. Okay, that is also summarized on the next slide. So you see here alternative ISO profit lines, and actually I think I have it already, I skipped the slide. So here you can see I have derived the ISO profit line for a profit of 80, which is here. And if I want to know what's the ISO profit line for a profit of 100, then I would have to shift that to the right to 10. And if I want to know what's the ISO profit line at 120, I will shift it to 12. But this is just here for 8. Okay. So technically, what we are interested in when it comes to the ISO profit line is really only the slope. And then we just take a straight line with that slope of the ISO profit line, and then we try to shift it as far out from the origin as possible. Okay, and then in the next slide, or the final slide, you can see in the graph 3 ISO profit lines. The one closest to the origin is the profit of 80. Then the one in the middle is the profit of 100. And the most outer one is a profit of 120. And you can see that we cannot reach the most outer one because it's outside the area of feasible production. So we can forget about this one. Well, we can realize this one here. Yeah, we could produce maybe 4 Nightingales and 4 Bernoullis, but then we would make a profit of only 80. But I'm better off if I produce 8 Bernoullis and 2 Nightingales, because then I would make a profit of 100. So the profit maximizing condition is given by the ISO profit line. It goes from 10 to 10, and which represents a total profit of 100. So this is how you solve a linear programming model graphically. Again, step 1, you draw all the constraints. Step 2, you identify the area of feasible production. Step 3, you identify an arbitrary ISO profit line, and technically what you need is the slope of that line, and then you shift that arbitrary ISO profit line from the origin as far out as possible so that you still touch the area of feasible production, or the production possibility frontier, and that will then give you graphically the optimum production. So okay, so let's just stop here and then let's replicate the same exercise using Excel. So I'll see you in the next video.